Welcome to Summarized Science, where we break down complex research into simple concepts. Today, we're looking at a paper from the University of Oxford that asks a fundamental question. How are AI models, like the ones that generate images, so creative? They can produce incredibly high-quality, novel samples that weren't in their training data, showing a surprising ability to generalize. A leading theory for this is called the manifold hypothesis. The idea is that real-world data, like all the pictures of cats, doesn't just fill up the entire space of all possible pixels. Instead, this data lives on a hidden, lower-dimensional geometric shape, or manifold. The AI's success comes from its ability to find this hidden shape and learn how to create new points on it. This paper argues that the key lies in how these models learn, specifically through a process involving smoothing. But not all smoothing is the same. If you smooth the data directly, it's like blurring the edges of the shape, and you get messy, off-target results, as you can see in the top row here. This is called data domain smoothing. However, diffusion models use a special kind of smoothing called log domain smoothing. As the researchers show, this method is geometry adaptive. It smooths along the manifold without falling off. This preserves the underlying structure of the data, allowing the AI to generate new samples that stay sharp and on target, as seen in the bottom row. This insight leads to an even more fascinating idea: geometric bias. The researchers show that by changing the way the smoothing is done, you can influence the very manifold the AI learns. Look here. Using the same training data points, different smoothing kernels cause the model to generate samples along completely different shapes. This means the model can be guided to interpolate or connect the dots in different ways. It's not just about finding one true shape, but about choosing a plausible one. This suggests we could one day engineer these models to generalize in specific, desirable ways. The scale of smoothing also matters. Here, with little smoothing, the model sticks to the fine details of the training data. With more smoothing, it learns a simpler, more general circular shape, and with too much, the structure collapses entirely. This shows there's a trade-off in finding the right level of generalization. To prove this isn't just for toy examples, the researchers tested this on the NIST handwritten digit dataset. In the top row, the score-smooth diffusion model generates novel images that are still clearly recognizable as the digit 4. In contrast, the bottom row shows that standard kernel density estimation, or KD, quickly devolves into a blurry, unrecognizable mess for the same level of novelty. This plot confirms it. As the generated samples become more novel and move away from the training data, the score-smoothed model stays much closer to the true manifold of 4s than the KD model does. So, to recap the important points, diffusion models are excellent generalizers because they implicitly learn the hidden geometric shape of the data. They achieve this through a special log domain smoothing process that respects this geometry, allowing them to create new samples along the learned manifold. Crucially, the nature of this smoothing can actually influence which geometry is learned, opening the door to more controllable AI creativity. This fundamental understanding helps demystify why these models work so well and could pave the way for creating even more powerful and efficient generative tools in the future. Thanks for watching.